pass to exercise 26. Which of the following electrons identified by their n and l quantum numbers has the highest energy? So they ask about the energy of the level, the energy of the orbital. We have n equals 3, l equals 0, so this is the orbital 3s. n equals 4, l equals 1. This is the energy of 4p. n equals 3, l equals 2. This is 3d. n equals 4, l equals 2. This is 4d. So as we know, as the electron is more distant from the nucleus, so as n increase, the energy increase. And the energy start with negative value till the highest value, so it increase in the negative to reach the value at the end E equal 0. So in this type of exercise, the highest n is or has the highest energy. So the highest n enter the energy. And the question, which has the highest energy? So we eliminate option 1 and option 3, state 1 and 3. So the choice is between n equal between 2 and 4. For the same n, when L increase, the energy of the orbital increase. So for the same n, the highest L has the greater energy. So 1 and 3 are eliminated. Between 2 and 4, they have the same n, but L in 4 is greater than L in 1. So the answer is 4. The answer is A. Exercise 27. Which of the following sets of quantum numbers could represent the last electron added to complete the electronic configuration for a ground state atom with the Z equal 33? So first of all, we have to write the electronic configuration for an atom X with Z equal 33, 1s2, according to Kleskovsky rule, we have two choices. Either we know the complete electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and till the end, or we construct the arrows rule of Kleskovsky. Then we follow the end of the arrow is the beginning of the second arrow. So 1s2, 2s2, 2p6, we have 10 electrons, 3s2, 3p6, 4s2, 10. So we have 20, 3d10, 30, 4p3. Suppose we want to add one electron. The electron is added on 4p3 because we have vacant site. But pay attention, this electron so is not what is the sign of the electron affinity. The question is, if we want to add by theory the electron, it should be added in 4p3 since 4p3 has 3 vacant orbitals. So the electron added will be added in 4p3. This is the rule. But if we talk about the electron affinity, we will say the electron would not be added easily. This is another question. So the electron will be added to 4p3. And as we know, 4p3, according to Hund's rule, we fill 1 electron in each box, then we redo the cycle. When this electron is added, the box representation 1, 2, 3, and now the electron added will be in the opposite spin of the first according to Pauli exclusion principle. So this electron added has a quantum numbers. First, it's added in level 4, so n equal 4. And in sub-level P, so L equal 1. So n equal 4, L equal 1. For L equal 1, what are the possible values of ML? ML between minus L and plus L, so minus 1, 0, plus 1, and the value of the spin is plus half or minus half. Can this electron be added in the second box? Yes. Can this electron be added in the third? Yes. But by convention, we put it in the first box. But it can be added to any of the 3 boxes. So the possible value of the quantum numbers of the electron added are 4, 1, minus 1, 0, plus 1 for ML, and MS equal plus and minus half. It depends. So we go to the proposed sets of quantum numbers. A is incorrect since the electron is added in 4. B is incorrect. So we have possibility of C and D since n equal 4, n equal 4. And L equal 1, L equal 1. ML plus half, it's possible. ML plus half, yes. MS plus half, yes. And MS minus half, this is acceptable. So C and D are acceptable sets of quantum numbers, and the correct answer in this case is E. Exercise 28. Give the corresponding atomic orbital for electrons with the following quantum numbers, NL, ML, and MS. And we have notations of this orbital. 2, 1 is to P. Pay attention that the notation of the orbital depends only on L and L. So 2, 1 is to P. 5, 3 is 5F. 3, 2 is 3D. So the correct answer is E. Exercise 29. What type of orbital is occupied by electron with the quantum numbers 5, n equal 5, L equal 3? So this electron is occupied in or occupy the n equal 5, L equal 3. So it occupies 5F. In 5F, how many orbitals do we have in 5F? As we know, the number of orbitals is the number of rooms, and in each room we have 2 electrons. So S is 1 orbital containing maximum 2 electrons. P is 3 orbitals containing maximum 6 electrons. D, 5 orbitals containing maximum 10 electrons, and F is 7 orbitals containing maximum 14 electrons. So how many orbitals do we have for n equal 5 and L equal 3? We have, this is 5F, so we have 7 orbitals, and the correct answer in this case is E. We can follow another rule. The number of types of orbitals is equal to the possible number of ML, and the possible values for ML is given by the relation 2L plus 1. So in this case, L equals 3. 2 times 3 is 6, plus 1 equals 7. So we have 7 orbitals. This is a rule that applies directly. The number of orbitals is equal to the number of possible values of ML, and the possible values of ML is according to L equal to L plus 1 values. Exercise 30. For an atom at the ground state, which of the following electronic configuration is correct? Pay attention for the question. For an atom at the ground state, so the electron distribution will follow the rules: Aufbau rule, Pauli rule, and Hund's rule. This is the ground state. Consider the electronic configuration in A. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. This is non-acceptable electronic configuration, since we know that we don't have d9, the electron will jump from 4s to d9. So the more stable electronic configuration, when I say the more stable electronic configuration, that means the electronic configuration at the ground state. The term ground state means the more stable electronic configuration. So the more stable is when we have orbital d completely filled. So the electronic configuration will end by 4s1, 3d10. This is incorrect. For B, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. By the same way, d4 is filled. It tends to be half filled d5. So we will have 4s1, 3d5, and B is also incorrect. We pass to C. 4s2, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d6. It's not acceptable according to Pauli rule to fill an orbital 3d if the suborbital 4s, suborbital as energy, is or has vacant place. 4s1 should receive this electron. So it should be 4s2, 3d5. It should be 4s2, 3d5. So C is incorrect. Now the student asked, why in 4s2, 3d9 the electron pass to D? So you obtain D10 and this orbital vacant. So why in this example we fill the 3D even for S is vacant or has one vacant place? This is another rule. This is the rule of half filled and completely filled. This is Aufbau rule in part C. So we have two rules completely different. We follow in A and B the rule of that D10 is completely filled, more stable than D5, more stable than the filled. So in this case, I can say this is the electronic configuration at the excited state. Or in other words, I excite one electron from 1s to add on D. So this is not the electronic configuration at the ground state. At the ground state, the electron should return to its normal position. So this is 4s2, 3d5. So C is incorrect. We pass to D, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. This is acceptable since D5 is half filled and this is the rule of half filled. So D is correct. The answer is D. We pass to exercise 31. In the ground state, pay attention for the question. They ask us the ground state or the excited state. In the ground state, that means the electrons are in their more stable places. Of Cobalt 27, what is the number of unpaired electrons? Unpaired electron means that this electron is single in the room. So first of all, we have to write the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So we have 20 electrons, then 3d7. We write the box representation for 3d7. In d orbital, we have 5 boxes, and we have to fill 7 electrons according to Hund's rule. We fill 1, 2, 3, 4, 5. Then we redo the cycle 6, 7. So according to this box representation, we have 3 unpaired electrons, 3 single electrons, and the correct answer is C. Exercise 32. The electronic configuration of chromium plus in the ground state is, we have several possibilities. So first of all, we have to write the real electronic configuration of chromium of the corresponding atom. So chromium has Z equal 4, 1s2, 2s2, 2p6, 3s2, 3p4, 4s2, 3d4. But as we said, 4s2, 3d4 is not the most stable. So we have 1 electron that passes from s to d4. So the electronic configuration ends by 4s1, 3d5. Now, the electronic configuration of chromium plus, we have to remove 1 electron from chromium. And as a rule, the electron removed is the electron the most distant from the nucleus, or is the electron on the higher level. So if we want to remove 1 electron, we have to remove 4s1. And if we want to remove the second electron, we start by removing from 3d5. So the electronic configuration of chromium plus ends by 4s0, 3d5. So the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And the correct answer in this case is B. Exercise 33. Consider the following atoms and ions. So consider the following species, which are isoelectronic with argon. Argon has Z equal 18. That means in argon we have 18 electrons. The term isoelectronic, A is isoelectronic with B. That means A and B have the same number of electrons. In Cl minus, Cl has Z equal 17. So Cl minus, we have 1 electron in addition. So we have 18 electrons. Mg has Z equal 12. So the number of protons is 12. And since Mg is neutral, the number of protons is equal to the number of electrons, and the number of electrons is 12. In phosphorus, Z equals 15. The number of electrons is 15. In K plus, K has Z equal 19. And how to obtain the electronic configuration of K plus from K? K minus 1 electron gives K plus. So the number of electrons in K plus is 19 minus 1 equal 18. And in cerium 58, we have 58 electrons. So the species that are isoelectronic with argon are the species having 18 electrons. So 1 and 4, and the answer in this case is B. Exercise 34. At the ground state, a ground state atom of manganese, Z equal 25, the number of unpaired electrons is, and we have to complete, is diamagnetic or paramagnetic. In this type of exercise, we write directly the electronic configuration at the ground state. Then we count the number of single electrons. And to remember, a single electron is an electron is single in the room. So this is a box of 1 arrow. And what is the meaning of diamagnetic or paramagnetic? An atom or species is paramagnetic if the electronic configuration contains at least 1 single. We can have 5, 6, 7, 2, but the condition is to have at least 1. This is paramagnetic. And diamagnetic, so in the electronic configuration, we don't have single electrons. We have only pairs of electrons. So unpair, and paramagnetic, this is true. Unpair and diamagnetic, this is false. So first of all, we write the electronic configuration of Mn: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. We write the box representation 1, 2, we have 5, 1, 2, 3, 4, 5. And pay attention, when you write electrons in the same orbital, this electron should be of the same spin. So you can write all arrows the direction from down to up, or you can write all arrows from up to down the direction of the arrow. But pay attention, you could not mix, for example, 2 arrows up and 3 arrows down. They should have the same direction. So the number of unpaired electrons, we have 5 unpaired. We have 5 unpaired. We need at least 1. So this is paramagnetic atom. And the answer is D. 5 unpaired, and the atom is paramagnetic. Exercise 35. A ground state chromium atom has how many single electrons? So we have to calculate, to write the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And pay attention, this is a trick. We have 5 unpaired in D, 1, 2, 3, 4, 5, and we have 1 unpaired in 4s. So the number of unpaired in this case is equal to 6. The number of unpaired electrons in the electronic configuration is 6 and not 5. So the answer is D. Exercise 36. Which of the following best describes the ground state electronic configuration of phosphorus atom? So we write the electronic configuration of phosphorus 1s2, 2s2, 2p6, 3s2, 3p3. So the electronic configuration is we have 10 core electrons from 1s2 to 2p6. That is identical to the electronic configuration of neon. So the abbreviation electronic configuration is P, neon, 3s2, 3p3. And according to Hund's rule, these 3 electrons should be filled in one box of P. So we have P, X, Py, Pz. This is the best representation according to Hund's rule. So the 3 electrons have the same spin. Previously, we said that in the same level, the arrows should be written in the same direction, or the 3 arrows up, or the 3 arrows down. So they have the same spin, ms. We pass to the proposal statements. A, neon 3s2, 3p2, 3p1. This is incorrect according to Hund's rule. B, 3s1, 3p2, 3p2. So this is neon 3s1, 3p4. It's not allowed at the ground state to have orbital P filled with electron and there is a place on S. So this is true if we can consider the electron configuration at the excited state. But in the question, they ask the electron configuration at the ground state. So this is incorrect. This is excited. This is electronic configuration at the excited state and not at the ground state. C, 3s2, 3px1, 3py1, 3pz1. Two p spin plus half and 1 spin minus half. This is incorrect. The 3 spins should be of same sign, either plus half or minus half. So this is incorrect. We cannot mix spins, sign of spins in the same orbital. D, 3s2, 3p1, 3p1, 3pz1, 3 spin of plus half. This is acceptable. And E, we could not mix the spins of different signs in the same box representation, so E is incorrect. And in this case, the correct answer is only D. Exercise 37. Arrange the following elements according to the decreasing atomic size, to decreasing R. So from higher to lower. These are elements. So in general, we have 2 possibilities. Or the periodic table is given. We can have directly, we can see directly their places according to the rows and the columns. Or Z is given. We write the electronic configuration and we place these elements in the periodic table. So I will suppose that the periodic table is given. Okay, we know that the atomic size or the radius increase from left, increase from right to left, from up to down. So rubidium Rb has radius greater than SR. and SR has radius greater than CA, and CA has radius greater than BR, and BR has radius greater than KR. So the order is RB, SR, CA, BR, KR. So the correct answer is C. Suppose in the given species we have atoms and we have ions. In this case, we could not use the periodic table. Why? The atoms could be arranged in the periodic table. But how to put ions in the periodic table? So in this case, if we have mix of species, atoms and ions, we have to use the principle of attraction. That means we write the electronic configuration of all species, then we look to n, to the distance d, the greatest d, that means the highest or the greatest size. For elements for the same d, we look to the principle of attraction. Do the species compared have different z or same z? If different z, we look to QQ prime. If same z, we look to the number of protons that attract one valence electron. So the number of protons per one valence of electrons. So in this case, when we have mix of species, atoms, and the ions, pay attention that we could not use directly the periodic table. We have to use the principle of attraction. Exercise 38. Which of the following has the smallest radius? BR 34 plus, AT 84 plus, BE 3 plus, carbon 5 plus, AL 12 plus. If we look to the number of electrons in the species, we observe that in BR 34 plus we have 1 electron, and AT 84 plus we have 1 electron. Iridium 3 plus also we have 1 electron, the same for carbon 5 plus and Al 12 plus. So all the above species are isoelectronic, and this species contain 1 electron. And we have a rule. For isoelectronic species, the greatest Z, the greatest attraction, so the smallest radius. So the order, the greatest Z is for AT 85, so AT has the smallest radius, so the correct answer is B. Exercise 39. Which element has the highest first ionization energy? Also, pay attention that the periodic table can be used only to describe IE1. If they ask about IE2, we could not use the periodic table. When we talk about IE2, so we transform X to X plus, then X plus to X2 plus. Okay, so we talk about ions, and the ions could not be located in the periodic table. So the periodic table is used only to describe IE1. The general trend of IE in the periodic table, The ionization energy increase in the opposite direction of the radius. The ionization energy increase up from left to right. And pay attention for the exception in the same row between group 2 and 3, between group 5 and 6. So all the given elements are in the same row. So the order is boron has ionization energy less than beryllium. So B less than Be, less than C. We have the exception now, less than O, less than N. So the highest ionization energy is for N. I repeat, we have exception between Be and B, and we have exception between N and O. So the order is the following: B less than Be, less than C, less than O, less than N. So the highest ionization energy is the highest IE1, the highest first is for nitrogen, and the correct answer is C. Consider exercise 40. Consider the following electronic configuration: krypton 5s1, neon 3s2, 3p5, 3, 4, 5. The question, which has the highest IE1? So now we don't have a periodic table. We have electronic configurations. So we have to arrange our elements in the periodic table. Therefore, we have to search for the period and the group. 1 is in group 1, period 5, or is in column 1, row 5. So we have to construct our periodic table. And the periodic table for block S and P is composed of 7 rows and 8 columns. Second, we put these elements in the period in this table, and we arrange, we follow the trends. So 1, I construct a periodic table. 2, 4, 6, 8. We have 8 columns for block S and P. 2, 4, 6, 7. We have 7 periods. So 1 is in a group 1, row 5. 2 is in group 7, period 3. Group 7, period 3. 3 is in period 4, 1, 2, 3, 4. And group 6. 4 is in period 3, 1, 2, 3. Group 8. 5 is in period 4, group 1. So we put the elements in the periodic table we construct, and now we follow the trends of the ionization energy IE1. IE1 increases from down to up, from left to right, and pay attention for the exceptions between group 2 and 3, group 5 and 6. So the order, the highest ionization 1 has ionization energy less than 5, and element 5 has ionization energy less than 3, and 3 has ionization energy than this box. So less than 2, less than 4. So the highest ionization energy is for element 4, and the answer is D. As a general rule, the rare gas have the highest IE1 and the highest EA1. Why? Since it's an orbital completely filled, it's difficult to remove electron and it's difficult to add electron. So as a rule, any element in group 8 has the greatest IE and IE1 and EA1. Exercise 41 of the choices below, which gives the correct order of first ionization energy. The periodic table is given. So in the same row, the ionization energy increase from left to right, with the exceptions. Okay. So the order is K less than GA, less than CA, less than SE, less than BR. So the correct answer is E. The last exercise, exercise 42, when we move from left to right within the same row of periodic table, the electron affinity will become more negative, remains constant, less negative, need more information. As a rule, the electron affinity is less negative in the same group from up to down and in the same row from left to right. So in the same row, the electron affinity from left to right will be more negative, and the answer is D, is A. The answer is